All right, so today we're going to talk about lecture number 4, threads. So last session we covered processes, representation of a process in operating system, creation of a process, termination, context switching, process queues, process scheduling, and inter-process communication. I guess if there is any question, you can bring it up to office hours. So this is the assignment. Again, I repeat and emphasize on this just to be done. And that is, make sure that you read the threads part of the Pintos manual and also the appendix A2. The manual is available at the resources, also in your own Pintos repository, available in your VMs. You can find it in the doc directory. If you run a make there, then it will get generated. And yes, so let's talk about threads today. So threads is again very similar to process, but there are the differences that today we're going to cover. So first we're going to talk about concurrent programming in some aspects, and then we talk about why do we need threads, not just like processes, and the differences between threads and processes, and a couple of examples from threading and how it is implemented, and multithreading models implemented in operating systems. We basically also talk about some issues regarding thread cancellation, signal handling, and thread pools. We're going to talk about them. So concurrent programming in general, we want to have the concurrent programming model because in a lot of cases we can speed things up, right? Instead, like an application, it's not necessarily sequential just like that, but it can benefit, or it's just like the functionality of the program is in a way that it is concurrent. Things are happening at the same time, right? And if things are happening at the same time and we want to use the sequential model, then we only have the time sharing model that we have covered. But there are some gains to concurrent programming. So the motivations behind this is that, first of all, you increase the performance. If you can do something at this, in parallel with multiple, especially with multiple processors, then it definitely is, you can speed up. So if in theory you divide a program in smaller pieces and run it n times faster with n processes at the same time. But there's also something with the independent physical devices, meaning if the usage of the program is to deal with different devices, and instead of like having only one thread of execution waiting for a device at a time, then different things can utilize different devices at the same time. So this is an example of how a serial and a parallel can work. Like if everything is serial and then there is all the execution basically halts and waits for the processor. But if the resources are available, then if you basically make it parallel, you get the job done faster, right? So as an example, we have one of the reasons is divide and conquer, right? So this is a divide and compute. So if we want to compute the addition of like 8 variables, how many operations with a sequential programming we need? It will be 7. This is an example because we need to do first add x1 and x2, and then once we have that, next step we add x3 to the previous result, and then once we have that, x4, 5, 6, 7, and 8. So in total we have like 7 steps of addition, right? But can we do it better? Yes, if we have parallelism and we can implement it, then we can. How? So instead of like running in one at a time, when we have a parallelism of 4 in the first step, because we have 8 variables that we want to add, so we can add 2 of them at a time. So basically we can have 4 additions at the first step, which is 1, 2, 3, 4. And then on the second step, now we have 4 things, values to add up, and we can add 2 of them at a time. So basically we have a parallelism level of 2, and then so we add each of these two into this, and these two to this, and then basically we'll be, you know, at the last step we only add these two. So the 7th step can come down to 3 steps. The additions are still happening. All of, you know, the 7 additions are happening. It's just that it gets done much faster in 3 steps. So the theory, if we have n processors and, you know, we can have our job to n smaller chunks, then basically we can result it in n times faster, to run it in n times faster. But that's not the case. In practice, you can't do this just because you have communication costs, right? If there are multiple processes or threads running at the same time, they have to communicate with each other and sync up. And there is also dependencies between different programs, so you can't just divide any program into the n execution, you know, chunks. As an example, as we saw, the addition example, if you have, like, you know, many additions, you can only run it in log n time, not just divided by n, right? Because every time you can make them half. So this is because this addition cannot happen before this or before this, you know, or at the same time. This is the dependency. So in concurrent programming, the implementation of concurrent tasks can happen as separate programs, right? Or as a set of processes or threads created by a single program. So this just depends on how the developer or has designed it. So, you know, if a program has separate programs, or basically it consists of separate programs, well, that's a different, you know, story. But if a program can use a set of processes or threads, then we're talking about this, right? So execution of concurrent tasks can happen either on a single processor, which then can have multiple cores. In this case, we call it a multi-threaded programming, because each process will be assigned to a processor, and then if that processor has multiple cores, that single process can have multiple threads running at the same time on those cores. If you have several processors, you know, working in close proximity, like, you know, server, for example, then you can have parallel computing. That's what it's called. And then if you have like several processors distributed across a network, that will be a distributed computing, right? These are just like different models. So this is the case that we're talking about it today, right? So why are we using now threads? Because in a certain case, a single application may need to run several tasks at the same time. It's not that it's different processes, but it's the same process but wants to do separate things, right? And it makes it faster when you have multiple threads running at the same time, that if the jobs can allow that, right? Basically, they're not depending on each other. And if you use threads instead of like processor, there's less overhead of creation and switching and termination. Because if you want to do separate independent tasks with different processors, last session we talked about fork. So you remember the fork process has a lot of steps, like you create the address space, and then you assign the whole process control block. But if it's the same process that has just like multiple tasks, basically it just needs to create thread. We're going to talk about it in the next slides as well. So the overhead is just like smaller. And the other benefit is that they share the same address space. So if you have one task and just multiple parts of it, if you create multiple processes, they cannot have access to each other's address space. So then you have to use inter-process communication, right? But if you have multiple threads, then they share the same address space. They share the same variables. They have shared variables as well as their own space, right? So the benefits of these is that first of all, it can like give the illusion of a full-time interactivity in some cases. So in a lot of programs, basically, you don't want the program to freeze up and when you type or move the mouse or something. And well, if the actual functionality of the program is something, and your input is means of giving it input, it's not that wise to periodically check for mouse and keyboard, for example, because that takes time. So if you increase that frequency for that and check for input every millisecond, then the overhead is just like too much. Like you're just checking for basically nothing. So instead, a thread can be there. A thread can be responsible for the user responses, and then the other thread can actually execute the program, right? So this is similar as what we discussed in time sharing. That was also something that gives the responsiveness illusion to the user or the programs, right? So the other thing is that it allows asynchronous processes. The execution streams, if they're independent tasks, then with using the threads, we are separating them. Again, within the same process, if there are just different tasks that can be separated and associated to different threads. So a thread, for example, can also handle other asynchronous signals, for example, events or client requests and all that. So a thread can start just like watch these events, and the other thread or threads may just continue execution, right? And the other benefit is just to increase the speed of execution. So especially there are two cases. If you have multiple cores that you can benefit from by using multiple threads running at the same time on multiple cores, well, you're basically speeding up. The other thing is you remember that we talked about IO-bound processes and CPU-bound processes. Now, within each process, we also have IO-bound task or CPU-bound task. Again, I made an example of a game that has let's say a game. There are tons of things going on in the game. There are agents, and then there's the graphics, and then there's the actions, but there's also the input of the user, right? So you don't want any of them to wait for the other thing to be handled, right? So the IO execution, the IO wait can be handled at the same time that the CPU is executing another thread, right? So these are some of these benefits of having and using threads. So in the case of this example we made in our first or second lecture, so when we are making a pasta, then the thread is the execution stream. So this is the whole task, this is the process, but we can have multiple threads do independent tasks at the same time, maybe communicate to each other, having access to the shared data, and that's basically what the thread is. So in this, the process has some data, some information with the PCB block, but the execution is thread. Look at the next slide. So this is like a diagram for how we can think about the thread. So if we have a single threaded process, the whole address space is there. This is something similar to what we saw in the last session's diagram. So there is code of the process, there is data, there are files. These are basically within the address space of the process. And then there is the registers for that process and the stack, right? This is what we saw. And the thread is the execution. So far that's what we've seen. Now, if you have a multi-threaded process, the process still has the data files and shared code or some pieces of the code that is basically loaded by the operating system there. But then you have the threads, not just a single one, but multiple. Each of them have their own set of registers and their own stack. Because now when this thread wants to run some pieces of the code, then it definitely wants to keep its state. so that if this thread stops or wants to resume, or if it wants to call a function within the code and move around in the code, it needs a stack. Now another thread also runs maybe a different piece of code, right? But this cannot interfere with this in the execution, and for the execution you need registers and stack. That's just what we learn in this case as well. Like each thread needs this register and stack to run. And so that's a bit of a difference. So let's go back to our diagram which we saw last session. So what we saw here in the context of the process was the process control block and a stack. So this was a single thread process, right? Now it has to change because this process control block has still the process identifier, open files and everything that we talked about. But we also need the thread 1 control block, the thread 2 control block, and etc. So each thread also has their own control block, which contains basically the information specific to that thread. And also, instead of a single stack, each thread should have their own stack, right? So in the case of a single thread, that would be just similar to this, but if you have multiple threads, each of them get their own, right? And the reason is each of them should have a running or block state because they can run at the same time on different cores, or one after another, when one is waiting for an IO, the other runs, and each of these threads have an state. And they, again, as I mentioned the example, each of them requires their own CPU registers in order to function properly. Continue, resume, pause, push, pop, call a function, whatever. And that's also with the execution history that they need a stack, right? So they also have the process control block is still there, right? So which you can find, for example, how many threads are there or something. That is also again now added to the PCB. We didn't talk about this because we didn't have multiple threads, right? So now there are in the process control block, there are some per process information, and there is now also per thread information, right? So let's see. So they're colored in red. So a process identification stays the same, right? Because we still have one process. But there are also thread identifiers. So the thread identifier is per thread. Each thread also gets their own ID. Now, CPU state information in terms of, again, registers, stack, and everything, these are also per thread. It's not just per process, per thread. And there are process control information that can be regarding the scheduling, which is a state, priority for getting scheduled, the waited event that is a thread is waiting for. These are also thread based. Because the OS wants to block or schedule a single thread at a time. Either this thread or this thread, they're separate. So that's for each of them. But the general memory space, the open files, pointer to the next PCB, so these are still per process. There's no need for defining it per thread. So now when we spawn the process, we remember that we needed to set up a process control block. The OS would do that, if you remember. And once you do that, the OS allocates an address space completely for specific for the new process, and then loads the program from the previous process or the parent process into the child process. And then passing the process control block to the scheduler so that it can basically resume or get scheduled, right? Now, with thread spawning is different because, none of that is happening when you create a thread, because the thread is created within the same process, and it belongs to that process. So you don't create an address space; it just shares that. All threads within the process share the resources of a process, including the address space, right? As we just saw in the last diagram. So the address space is going to be the same. All the threads have access to it. And scheduling is performed on a per thread basis, right? So each of the threads can be scheduled or the other one. And basically, it's a more, we say it's a finer grained scheduling model than the process model, because the overhead of also switching is not that much, and it can happen without changing all the memory space, for example. And the life cycle, though, it's very similar to the processes. They get created, they get ready, they go into running, and then it get terminated. But it's just like, again, within the same process, we have multiple threads, right? So now, if you want to compare the threads and process, it's an analogy that you can think of, that a heavyweight process is called a process, and a lightweight process is called a thread. Again, this is not very accurate, but if we have a heavyweight process, if we can divide it into light-weighted processes, then those light-weighted processes are threads basically running, and the whole heavyweight task is the process. So what are the advantages and disadvantages of using threads? So for advantage, the first thing is that it's much quicker to create a thread, because again, you don't have to create a whole address space and assign all the allocate all the resources, right? So it is also quicker to switch between threads, again, because if you're switching from one thread to the other thread, maybe you don't have to change all the memory space. And they also, this is also very important, threads share data easily. So if you have a process, a task, that as a designer you want all the process have access to shared data. If you use different processes, it just makes it more difficult, because you have to use either specific shared memory access or use IPC. But the threads basically share the data that you want. And disadvantages is that processes gives you more flexibility, just because we will see if there are multiple threads within a process. If one terminates, for example, what will happen? If one crashes, what will happen? And this also gives you the flexibility of running them on multiple processors at the same time. And well, the security is also an issue. Well, you are the programmer, but still, one thread can stomp on another thread's data, because they have access to each other's data. So they can also, that causes security. And so we're going to talk about also some threads, but some of the threads are in user space only. They're not basically backed by the kernel. So there are multiple threads, but they're not backed by the kernel. They just run in the user space. And basically, if one of these threads get blocked from the point of view of the kernel, that process is blocked. So all the threads gets blocked. So this is not that useful in terms of concurrent programming. So, but that depends on the model. So here, this is two important functions that you need to know about the thread. Okay. So first is how a thread gets created. So pthread, it's basically a library that we're gonna use, and it's also, I think, used in your Pintos. So the way that you create a pthread is that you assign an integer, because that will be the PID, and this is the function name, pthread create, and then you give it the thread name and the attribute that is required, the function that it needs to call. This is the pointer to the pthread variable itself. Where's the name? The name, I think, is not in the, that should be probably in the attribute. And the arguments to that. So when you want to start a thread, basically you want that thread to do something. That something is a function and some arguments, right? Or the main function that you want to basically start, right? So this is the arguments that you put on the stack for that main function, and this is the start routine, or the entry point that you give it as a function pointer. And so these attributes are the other things, again, the name of the thread or so. So now another important function is the pthread join. Again, this is important. So the pthread join suspends the execution of calling thread until the target thread terminates. So this basically is when you have multiple threads and you want to wait for another thread, you call this join, pthread join, on that thread. And we'll see why. So last session we kind of saw what is the process wait. So if a process, for example, a parent wants their child process to be done, right? They don't want to terminate before that. They want to, for example, wait for the result or error or something. They wait for a child. So in the threads, you can wait for another thread. This can have like different reasons. One is that you want to, again, make sure that they are, you know, what is the result of their task, what is if there is an error. And then you also, or you want to just like wait for them to finish before the other thread, this thread finishes, right? So just remember that this the pthread join and pthread create. So you wait for a thread by giving the pthread join the thread ID. I mean the thread variable. This is the thread type. Okay. And you also give it a pointer so that it saves you know, the returning value in there, right? So this is an example, and we're going to talk about the create and join. So you define two thread variables of type pthread, and so because again the threads have an ID, or you know they have there are ways to point to them, but they're of type pthread. This is a, you know, a struct. And so when you create a pthread create, you give the reference to the thread 1, and there's no attribute that we want to give to it for now, and this is just not null. And then we call a print message function. That's just like, imagine that is a function, and we basically this way you cast it into a void star. Again, it should be a function pointer. So if you're not familiar with pointers or references, you've not like programmed in C, it's fine. You should like figure these out in recitations or office hours, or just catch up a little bit by, you know, by online resources. But a pointer to a function is when you just define a function. That function you can get its address basically by this reference, and then when you cast it to a void star, then it's just like a pointer with no type. And so the argument that you want to send to that function, remember that function is a printing function. So the argument to that function is something like in a string, right? Well, here we're giving it like a string of hello, but we should cast it to a void star just because that would be the responsibility of the print message function to get this argument correctly. This is argument. This is not the variables or argument that are passed in a function when you call them. This is like argv and argc, if you have like worked with them. If when you call a program and then you give them parameters, all of that will just be in a string mode, just like that. And then it's the job of the process. So for example, when you say ls-l, which gives you the list of the files and lists them, you know, in Unix or Linux, you're basically calling ls, and the argument that you pass to this program will be ls-l, right? And the ls program itself at the start of it will read its own arguments to see whoever that called it, what has passed, right? You'll deal with this in detail in your project too. But anyways, for that, ls then decodes it. Now, it sees the -l, then it realizes that, oh, the user wants me to print the listing the directories in this manner, so it does that. If that includes an A, then it also wants to, you know, list them, all the files, including the one that have like this dots in the name, whatever, right? Or if there's an H, it prints out the hiddens as well, right? So That's just like the arguments. So and then you create two thread variables. When you pthread creates runs, basically, then this thread struct, now you can expect it to refer to the thread 1. Now the thread 1 gets executed, starts executing this function. And then same, the pthread creates thread 2, again the same function but a different argument, right? Now at this point we have 3 threads. One is the main thread that is started. At this point it creates the second thread. At this point it creates the third thread, right? And remember that each of them now can get a scheduled in or out, and we cannot rely on any order. So maybe this thread gets finished and calls the exit if we don't call these, right? Maybe the thread like thread 1 gets executed and then prints out hello, and then this one gets printed world. Maybe reverse. Maybe this one runs first, prints world, and then this one prints hello. We cannot guarantee any of these. But we can guarantee one thing. If this main thread calls the exit, it exits the whole process. So if by this point none of these threads have executed, they won't. And that's why we need the pre-thread join, right? So because this thread wants to exit eventually, but it doesn't want to do that before the other threads are done, it calls join on them. So this call only gets finished if the thread 1 gets finished. So once thread 1 finishes and printing hello, then it can move on to the next line and wait for thread 2 so that it prints world. Then when both of them are done, then we can exit and be done, right? So the reason that we use pthread join is that to force the main block to wait for these two before exiting. Otherwise they might not finish. Remember, by this we are not guaranteeing the order of execution between these two. We are waiting for them in this order. By the time that we are waiting for thread 1, maybe the thread 2 already finishes. Then we immediately, skip this line because it's finished. But at least by running both of them, we can make sure that we wait for both of them. All right? So this is an exercise, and we're going to go over a simple example. So consider there are two threads, T1 and T2. There is a shared data, x is 5 and y is 10. Now we have two threads running at the same time. Thread 1 has the code y equals x plus 1, x equals y, and then print x. In thread 2, we have u equals y minus 1, and then y equals u, and then print y. So assume that each assignment statement on its own is executed as an atomic operation. This is important to know what is an atomic. We're going to talk about it in synchronization. But in brief, atomic operation is an operation that doesn't get intervened, right? So during this subtraction or addition here, the threads, they don't get intervened, right, or interrupted, right? But between the execution of different lines, they can, right? So for example, we can start with this thread run this line, and then it gets paused and this thread runs. It then can run this line and this line, but not this line. And then this one resumes. Then it starts this one. And then it runs this one. And then it runs. Any of these lines can run or interleave, right? You can have any order between these 6. Well, not any order between these 6. This definitely happens after this. This definitely happens after this, right? But you know how it works. So what will be the outcome? The possible outcomes. An example. X is 5, y is 10. Let's say if this one runs completely and then this one, right? So y would be x plus 1, so 6. X is also 6, so we print x, which is 6. And then this one comes. Now at this point, y is 6. So y negative 1 is 5, u is 5, y is 5, print 5. So that will be 6 and then 5. Now let's see if we run this one and then this one. At this point, y is 10. So u is 9, and then y is 9, and then we print 9. And then we assign y is 6, x is 6, then printing 6. So 9, 6. So the output can be very different, right? Actually, we can have like all like these different values. We can have 6, 5, we can have 5, 6, we can have 5, 5, 9, 9, 6, 6, 6, 9, 9, 6. All of these can happen, right? You can go back and then try different ways, like, you know, this one, and then this one, and then this one, and then this one. So this is important because later on, if you don't want this to happen, if you want to guarantee a flow of execution that does not happen, either they should not have this dependency, or if they have access to shared data and that they're modifying that, then you need to do some synchronization just to make sure your execution flow happens. So another example, a real example is a web server. So a web server is a process. It wants to handles requests from clients, but it definitely cannot do it with a single thread, right? So what it does is that they have a dispatcher thread, and then that basically accepts the request and then gives them to a worker thread to handle those, right? So that's like if you request a server from multiple clients, initially the dispatcher accepts them, and then and then handles a new thread gets created, and then that handles each client, right? So basically, this is what's happening. The kernel space is here. The network connection comes. This tells the process that there is a coming connection. The dispatcher thread is there accepting it, and then giving it to different worker threads. And then this is an example like how these basically form the web page. And so the important thing is now each of these threads they have a short task to do, right? To handle a request or response. After which they can be discarded. That thread just like gets created, get it done, and then terminated. Or they can be recycled, in what we call a thread pool. So a thread pool is we're going to talk about it in the next a couple of sessions from this, but just remember that you can use the same threads basically. That's the idea behind the thread pool. That would be a pool of different threads. When you have available threads and you need one, you just pick one out of the pool, and then that gets the job done. And then once it's done, it goes back into the pool, waiting for another work. So a real example is a word processor. In a word processor, you need multiple threads because one should respond to the keyboard or the interaction of the user. The other one should be actually running the spelling check or forming of the words into the pages and everything. And then periodically one might want to autosave this to the disk, right? These are different threads running at the same time, fairly independent. So the implementation of thread now, we have like different models. So one is the user level threads, which is called ULT, and then the other one is kernel level threads. So that's what we talked about in the past, in a few sessions before this, a few slides before this. So if you implement all the threads within the user space, then there is one thread of execution, within the kernel, and then in the user space you have a threads library that then you have like different threads that can run basically different parts of the code. Now, if you have all different threads implemented in the kernel, you have different kernel threads that can run the different pieces of the same threads in the user space and run at the same time different pieces of code. And you can also have combined them. You can have a combined model of multiple kernel threads and then having multiple user threads and how they're gonna match to which one. So in a complete user level thread, the kernel is not aware of the thread itself. The kernel doesn't know. The kernel has one execution thread, and then basically each user process manages its own private thread table. So if kernel wants to basically run this thread, then the process decides that, oh, okay, now this thread should run, or this one, right? So the process that they're light thread switching because it's handled in the user space. There is no overhead in the kernel, and you don't need to also go to kernel mode privileges or do any of that stuff because the kernel keeps it simple. Now it's also cross-platform because everything is in user space using maybe the same library or just like the library depending on the OS. The ULTs you don't have to change them. They can run on any OS. Now the cons is that if a thread blocks, the entire process gets blocked. Remember, there are multiple threads and a single threading kernel. So if a thread gets blocked by a system call, for example, then this thread cannot run. This is blocked, and once this is blocked, none of these can run. So this is the implementation of the user level thread. So the kernel keeps it simple. It only keeps the process table, and then each process keeps their own thread table, and they have their own runtime system that then decides which thread to run. Now in a kernel level thread, it's different. This is the case in most operating systems, which basically the kernel knows about and manages the threads by itself. So each kernel thread is handled within the kernel, and each thread is basically a kernel thread, meaning the operating system manages them. And if a thread is blocked, it doesn't have anything to do with the other thread. So if a user have multiple threads assigned to different kernel threads, then they're basically independent, right? So this is the same thing that we've seen, but instead of like process scheduling, it's finer because it's now thread scheduling. And this is again this is the downside of the previous one. This one doesn't have that. The cons is that because they are all in kernel, the heavy thread switching involves mode switch within the kernel. So it's just like more overhead. So this is the diagram for that. So the kernel itself keeps the process table as well as the thread table. So that is the information about all the threads. And so then decides, which each thread basically has their own each thread is managed basically within the kernel, right? Brain freeze. All right, so now we have different multi-threading models. So whether the within the kernel, if the implementation of the threads are within the kernel, then how are user threads assigned to kernel threads? So we have a many-to-one, we have a one-to-one, and many-to-many, and then there's like always the hybrid combination there, right? Or we call it two-level here. So let's see what it means. So in a many-to-one model, it's that you have many user threads assigned to a single kernel thread, right? So this mapping means that thread management is happening in the user space. So the user space basically decides that this kernel thread is which one of these is mapped to it, right? Now the problem is, again, like the previous example, if this kernel thread blocks, all of these will be blocked because all of them are mapped to this single thread, right? So this basically limits the parallelism, especially in the case of when a thread can get blocked. And or the use I/O. Again, whenever a thread wants to access kernel for any reason, the others basically cannot. So this can be in the case of an I/O or interrupt or system call. So these are a couple of examples of this model, implementation of threads. So we have also a one-to-one, which again, this is something that you might, use or make more sense to you just because it's what you use, and that is like each user thread is assigned the kernel thread. So this does not have the downsides that we showed for in the last session, in the last slide. So all can access kernel separately, and so there's only the drawback, which is that when you have all this in the kernel, the overhead is too much, right? Creating a user requires a kernel level thread, and that increases the number of threads that you can have, because this requires resources and the memory within the kernel. So that limits the number of threads. You can technically have many user level threads. That's the user program. But if each of those need a kernel thread and resources within the kernel, then as your user programs grow, then the resources used within the kernel also grow. So that's the downside, right? So there's also many-to-many, which is basically somewhat like there are different threads and there are different kernel threads, and each of them can be assigned to each of those. And this basically allows the operating system to have sufficient number of kernel threads and have this satisfy the parallelism as well as efficiency. Well, we're going to talk about the next one in the 2 level, right? So this allows the kernel to limit the number of threads, so it doesn't have, if you have like 1,000 threads here and 4 threads here, for some reason, maybe you only have 2 cores, so it doesn't make sense to have 1,000 threads. But now the operating system decides which of these threads are going to run, and then they assign it to that thread. So if this thread is not running, if it's like blocked, then it doesn't assign it, map it to this kernel thread. So it just like waits there until it's ready. But this way has the flexibility of using the concurrency within the kernel, but also not having the drawback of the previous one. So the two-level model is similar to this, very similar to this. Basically, it allows the OS basically decides how many kernel threads it can have based on, again, many things, like for example the number of cores of the process, and I guess maybe the memory. But it also allows a user thread to be bound to kernel. So for some reason, if this user thread is bound to this kernel thread, that's the difference. So again, this is in not very famous or popular operating systems, but it just did that. The reason could be, for example, if this thread has it uses a lot of kernel resources, or wants to run many times, or with a high frequency in kernel mode, or has a high priority. So that would allow that. All right. So the thread pools that we talked about is when each of the creation and termination, there is an overhead. And you don't want that, especially if a thread has a short task, right? So if you start like creating all the threads, and then this can exhaust your system resources for no reason, without you doing useful work. And so what they do, like a web server again, is that they create a number of threads at the startup. So and then put them in a pool where they await work. So depending on the system resources, maybe you create 1,000, maybe you create 100, right? And then that decides that, okay, this web server can handle 100 requests at the same time, right? So that limits it, because if you don't do that, and if a request comes and you create a new thread every time, then what happens if 1,000 requests come at the same time and you only have resources for 100? Basically the capacity, right? So then it will just like, you know, crash it or, you know, freezes. So this allows it to have 100 thread available. So if there are 100 requests at the same time, it handles. If there are more than that, well, they should wait, okay? It kind of like keeps the system running, right? And it also is really much faster to service a request with an existing thread rather than creating and then, you know, terminating again. And again, it keeps the number of threads that limited, basically. So there are a few questions that might now raise here. So what happens with the fork and exec, right? We talked about this last session in the process lecture. And so a fork was when a process wants to duplicate itself, right? And the exec or exec v is when a process wants to replace its code with another program, right? So now the question is that when a program, when we were like talking about the single-threaded program. Now, if a multiple-threaded program calls a fork, another process gets created, but should it also contain all the threads of this one, or only the thread that's called the fork? Because the fork was called only by one thread, right? So that call copies the whole process to a new process. So with the same data. So the data is the same. It's fine. But this one now has multiple threads. One of them called the fork. What should be the case of here? Should it copy the rest of the, you know, threads as well, or just a single one? So it's that, you know, in Unix system, for example, the implementation of both is there. It depends, you know, it allows you to decide. So if first we're going to talk about this and then. So if a thread execute exec system called, remember the whole process was replaced by another process. So this is going to be the same. So you can't just replace one thread of a process with a different process. You know, program, code, and everything should come. So once you call the exec, all the process will be gone. So now this will tell you, if you are calling a fork, and then immediately, for example, in the child process, you're calling exec, that is the case of an example that we saw last session. So if you're calling a fork and your parent process continues, and your child process immediately in the if conditions realizes that okay, I'm the child process, so just go and call exec v, bring that program. So it doesn't actually make sense to fork with all the threads, because that single thread that ran that fork within the next couple of lines of code will replace the whole process, right? But if for some reason you call the fork and the new process wants to just run, then it may make sense. Maybe you want other threads to be copied as well and do something else, or they use still. So this is the case that Unix gives you both options. So in terms of a thread cancellation, so you can cancel a thread or terminate it, right? So you can terminate a thread before it's done. Why is that? Well, so if a thread is doing a job which is parallel to another thread, once the one is finished, the other one is not needed, right? So an example is that, for example, if you were searching a database for something, right? And once it's found, you don't want the other threads to keep going. Let's say in this room, we want to look for a phone. And then I will say, okay, I'll search this half, and then you'll say, okay, I'll search this half. Whenever you find it, well, you'll tell me to stop. That's the exact thing happening here, right? Or here an example of the web browser. In your web browser, there are multiple threads running, right? One is loading the page, one is loading, different requests, HTTP, whatever. One is handling maybe something, playing in a different tab. And once you close it, once you press the button, on a browser that, go to a different page, then all the other threads, they should stop. They should not download more content. And then basically, it basically continues with the new request, right? So it depends on the functionality of what you want to do, but this gives you the ability to stop it to prevent more waste, right? And there are also two ways to request a thread or stop it. So there is asynchronous cancellation, which terminates the thread immediately. So if you tell me, okay, I found the phone, stop. That's it, I stop. But the example would be a little bit, let's say, okay, let's say we're looking, like in all the drawers. In all the drawers, if I open and then close, if I'm looking for something and opening and closing, and then when you find something and say, okay, I'm done, well, if I just stop it, then that drawer might be left open, right? It's a little bit different. You see, in the phone case, I was not using any resources, right? I was not leaving any footprint, basically. But in this case, even though I may not want to continue search, but I may still want to do something before I stop, right? And this is the case for deferred cancellation. So it allows the target thread to periodically check if it should be canceled and then cancel. So in this case, well, when the thread itself will be, looking for a deferred cancellation. So you will give it a signal that, okay, you should stop. There is no need for you to do anything else. At least, for whoever is decided, there's no need for you to do anything. Now, the thread itself, when it checks for that, it realizes, oh, okay, I don't need to do execution. Now I need to wrap up or clean up or whatever, and that's why it's like, it's safer. It doesn't leave footprints, or it doesn't leave any corrupted file. For example, if a thread wants to update a file and then the other thread wants to kill it, then it wants to ensure that at least, okay, I want to save my latest updates to the file. So. But again, it's not that this is necessarily better. It depends on the function. So there's also signal handling in Unix where a process can signal another process, right? So the simple one is always when we control C and then kill or stop a program, right? Within the shell, when you run a program and you hit control C, that control C is caught, and then it will generate a kill signal to the process, and then the process basically handles that by stopping. So I mean, the signal handling might be that there are always implementations, the default implementation of the operating system, but also it can be handled by the process, right? So in a single process or single thread execution is straightforward, right? You have a single thread, and then you have the signal handling code, and then that thread runs it, right? But if a signal is generated and delivered to a process, right? How it is handled in a multi-threaded system, right? So you can deliver the signal to the thread to which the signal applies, if you know how to, if you know which one. You can deliver the signal to all the threads in the process. You can deliver the signal to certain threads in the process, and assign a specific thread to receive all signals for the process, and then just give it this, call it like the signal handler, right? These are just like different options. So in this case, basically, if a signal, if for example a thread has accessed memory address, right? And now that should basically that causes a signal, right? And it's not. I mean, the operating system knows which thread caused this, right? So it can just like send that signal to that single thread. Now, if you have multiple threads within a program and you want to close the whole process, you can send the kill signal to all of them. Now, each of them should handle them separately. Or if they have a single, I mean, if it is implemented like that, if a thread just receives all of them, and then that communicates with the rest of the threads, about how to handle that, if they need to do anything or stop. Or you might want to send it to all the threads, but some of the threads might block them. So some of the threads might block some kinds of signals so that they don't get them or handle them, right? So in that case, the operating system checks which threads are not blocking those signals and then just hands them to those, right? So this is again the difference between a multi-threaded signal handling and single thread signal handling. All right. So I hope the slides were clear. Take a look at the slides at home as well. Make sure you study them as well as the chapter 5 from the book. If there is any questions, bring them into class next session as well as office hours. Before recitations on Tuesday, we're going to have a class, so come prepared. So it's basically time to start, getting familiarized yourself with the threads code, because that's where you need to basically explore and modify the code for Pintos. At this point, do not make any modification, do not make comments or anything, because you have to first, share your repo and then start making comments. Otherwise, you might have merging issues. But at this point, at least you should know. You should read and understand what are the pieces of you can follow at least, how the code runs, jumping from functions to functions. And this is important. It's not just reading material as if, that you should ignore. No, go ahead and read chapter 1, chapter 2, appendix A1, A2, and A4. Also take a look at appendix C and D. These are all become useful, all right? So we will soon, today or tomorrow, we're going to put the instructions for you to start joining GitHub Classroom. Just follow the instructions. You'll have to join the classroom. You'll get notification, and then you'll have to go there, coordinate with each other first. One member of each group should create the group, and then the other members should join it. Pick a name for your group. Make sure it's unique. Don't pick, Pintos, for example, because the others, then it would be Pintos 1 and Pintos 2. Try to pick something unique. Make sure it's reasonable. It's not too long. It's not just like 1 or 2 to 3 characters. Just pick something. You can also take a look at the previously generated groups and then create something which doesn't, overlap with those, right? All right. So see you next session. If you have any questions, bring them to class.